All right, so to continue from last time, we were talking about binary search. And just to, in contrast to linear search, remember, you just start at the beginning and you go through for each element until you find what you're looking for. You're just looking for the needle in the haystack. Binary search has the potential to be much faster, in fact, exponentially faster. Because it exploits structure that you can impose on an array if you sort it. The idea is that you look at the middle element, remember? Because everything to the left is, because everything to the left here is less than that middle element, and everything to the right here is greater than that middle element, what you can do is you can exploit that structure by checking the middle element. If that middle element is the thing that you're looking for, you're done, right? Just stop, because that you've found a value that matches your criteria. Otherwise, if it doesn't match your criteria, then you at least know where that element is. Remember, we are on Piazza and we are on YouTube, so if you have any questions, go ahead and post there. Otherwise, if the element is less, then that means that you can just go over to this half of the array. If the element that you're searching for is greater, then you can go over to this half of the array. In either case, you've cut the array in half. If you had 1 million elements before, you've cut out 500,000 of them, and you don't need to make all these comparisons over here. You just need to focus on one. You can do that again. Jump to the middle of that cut in half array, all right? And you do this over and over again until you get to an array that is empty, right? Your left and right indices have passed each other, and that array is now empty, and you know that that was an unsuccessful search. Again, it's a classic divide and conquer kind of algorithm approach. Last time we went with a recursive implementation. What I want to do is I want to show you a non-recursive implementation, and then we'll do a halfway between a formal analysis and a hand-wavy analysis of how this algorithm works. So over here I've started out with this binary search. Remember last time it was binary search recursive, in which we passed in the left and the right left and right indices, which you experienced yesterday in your lab. When you looked for whether or not something was a palindrome, you started with this index over here and this index over here. But in contrast to binary search, all you did was move one over. Are these two characters the same? If so, recurse. Are these two characters the same? Are these two characters the same? Until you met in the middle. With binary search, you're basically doing the same divide and conquer strategy, but you're cutting out half of the array each and every single time. Okay? So let's do this in a non-recursive way. You don't have to pass in left and right as long as you keep track of those as local variables. Just go ahead and create a left index and start it at 0. Go ahead and create a right index and start it at, where's the rightmost element in an array? If we start at 0, then the last one will be where? n-1. Now, in our original version, we didn't have to pass in the size of the array because left and right were taken care of for us. But now we do, right? Int n. That's going to be the size of the array, okay? I think I also need to now update my, yep, here we go, int n. There we go, that is my prototype in the header file here, okay? All right, now, how are we going to go about this? What was our base case up here when left and right had passed each other? So while left is over here and right is still over here, and they meet in the middle somewhere, even when they're equal, I still want to check that one element. When they go past each other, that's when I want to stop. So I'm going to flip the condition here. While left is less than or equal to the right, I will keep checking, right? Is the middle element, is that the thing I'm looking for? If not, then cut it, cut it, cut it, cut it until they go past each other, breaking out of this while loop, and you know that you did not find the element that you were looking for, so you return -1, which is what we did up here. For an unsuccessful search, we return -1. All I'm doing here is flipping the termination condition. Right? Okay, well, what did we do up here as far as checking the key? Well, we still compute the left and the right index, the middle index here. And again, this is bad in practice. Do not do this. If you're interested in why, then read my book on it. I don't know if it covers it in Zybooks or not. In any case, this is susceptible to overflow. The proper solution here would be to go with left plus, that's where you start, and then right minus left divided by 2. In fact, that's good enough that we can leave it like that if we want to. But I'll just go ahead and go back to what we had originally. Again, in practice, you don't want to do that, okay? In practice, however, you're not rolling your own. You're not writing your own binary search, and we'll find out why later on, okay? All right, so if that's the thing that you're looking for, then stop, right? You don't need to break out of this while loop at all. Just stop and return the index at which you found it, m. Just like we did up here. We returned m. Otherwise, and here's the next condition, if the thing that you're looking for is less, right, than that middle element, then where do before we recursed in the left half. Now, instead of recursing in the left half, I'm going to keep the left index the same, but update the right index to be m minus 1. So right is equal to m minus 1. Else, if the thing that you're searching for is greater than that middle element, and again, that's not, strictly speaking, that's not necessary. You can go ahead and get rid of it. In fact, in this version, I will, right? Because it's either less than, greater than, or equal. There's no fourth condition here. I will update left to be, remind me, what was it? M plus 1. Good. M plus 1. There we go. And that's the end of the while loop. Right? Once those get past each other, then it breaks out of the while loop and returns -1 for an unsuccessful search. So let's go ahead and test this, make sure that it actually works. Instead of calling binary search recursive, we'll go ahead and call it on the numbers. And the size is n, and there's your key. We should be able to find this at the same index as before. I think we're searching for 42 here, and so all three of these should now return the same answer. Remind me, why didn't it work on this input right here last time? Because it wasn't sorted, it wasn't in order. If you're searching for something and you assume that it's in order, and the thing that you're searching for is, if it were in order, is over here, but it happens to be over there, your assumption is no longer correct. Right? All right, let's go ahead and see if this works. Search, oops. GCC, search.c and demo. I'll just go ahead and put them together there. Oops. Okay. GCC, I'll just do everything together. There we go. And let's run this. There we go. So 42, found at index 7. 42, that's the recursive version, found at index 7. And here's the non-recursive version, index found at 7. Now, if you were to rigorously test this, what would you do? You would search for everything, including things that don't exist. 412, say. And this should return -1 for all three of these because, of course, it's not in there. All right, great. Let's talk about analyzing this algorithm. Now, this course does not focus on algorithm analysis. That's a topic for computer science too. But let's think about it. So what I'm going to do is I'm going to set this up as a number of iterations. How many iterations does this while loop, right? Let's go back over here to this version. How many iterations does this while loop execute, right? How much work does each iteration do? So let's go ahead and think about this in those terms. Iteration. Let's think about the first iteration because that's concrete, right? The first iteration has you looking at an array of size n, and you make a comparison. So the size of the array is going to start out at n. Oh, sorry. Thank you. Just yell at me if I screw up like that. Sorry. The first iteration, the size is n. How many comparisons, number of comps, do we do on that first iteration? For that, let's go back to this code here. All right, well, I'm doing some work here. I'm doing an addition, I'm doing a division, but okay, that's necessary for the control structure of the algorithm. I'm doing a comparison here, and I'm doing a comparison here, and before I deleted it, I was doing a comparison here. Right? So technically, before I was doing 3 comparisons, I was able to cut that down at least to 2 comparisons. Strictly an equal equals, and then a strictly less than. For simplicity, I'm going to roll those 2 up into 1 comparison. Because at the end of the day, If you really want to consider this as two comparisons, you can go ahead and put a 2 up front here. The 2 is not going to matter. Right? So each iteration is going to end up doing one comparison. Now on the second iteration, what is the size? Suppose that we're looking at a worst case scenario here, so suppose that it's an unsuccessful search, that I maximize the number of iterations of this while loop. How big is it now? Well, I either found what I was looking for, I got lucky. I don't want to consider getting lucky all the time. Or I cut it into this half or cut it into this half. In either case, if it was n before, what is it now? N divided by 2. Right? Now, on that iteration, I make the same comparisons. Is this the thing I'm looking for, or is the thing I'm looking for over here, or is it over here? Right? I'm rolling those two comparisons into one comparison. Right? On the third iteration, before I had an array of size n divided by 2. If I cut that in half again, n divided by 2, do the math for me. N divided by 4. Oops. And I only make one comparison on that iteration, again, for the same reason. 4. How big is the array now? N divided by 8. And you make one comparison. Dot, dot, dot. On the kth iteration, we're just going to generalize this now. How big is the array at that point? Do you see the pattern here? All right, so 2 to the k minus 1 technically.
Oh yeah, sorry.
Excuse me. Why? Because on the fourth iteration here, this is going to be 2 to the third. 2 to the third. On the third iteration, this is 2 to the second. Right? Again, I don't like dealing with those pluses, minuses, whatever. So let's just go ahead and consider it and simplify. Simplify to n divided by 2 to the k. Right? Let's forget about that minus 1 for now. Right? And again, I do one comparison. Dot, dot, dot. When does it all end? When you have an array, technically, when you have an array of size 0, right? That's when you break out of the while loop and you move on. But you don't do any comparisons on that last iteration because there is no last iteration. Once you've broken out of that while loop, you simply return -1. So let's back up one step here. And on that last iteration, on that last iteration where you've got an array of size 1, you do perform one comparison in order to see, is this the thing I'm looking for? Left and right have now met, and you are asking, is this the thing I'm looking for? Right? If not, then go to the left, go to the right. In either case, you end up having your left and right pass each other. All right? So the question becomes, how many times do I add up 1, right? What is the total sum here? Okay. The sum is equal to k, the number of iterations you perform, right? Let's look at that from the perspective of the following equation. Again, the size of the array is n divided by 2 to the k, where k is the kth iteration, right? When that hits 1, you are done with the algorithm. So when does that happen? Solve for k. Dot, dot, dot. So I can take the denominator onto the other side. That's simple enough. How do I get rid of that 2 to isolate k? Take a logarithm on both sides. Logarithm of 2 to the k. And by the way, what base of logarithm do we use? Again, we're self-respecting computer scientists, so we always go with 2, implicitly. 2 and 2. In fact, that's the only way to get rid of k. Right? Log base 2 of 2 to the x is going to simplify to x. You can look at that as taking this, that's a log identity, and you can take that out to the outside, and then log base 2 of 2, those cancel out. Just like the natural log of e becomes 1. Right? All right, so bring this down, log, and here I'm not going to write base 2 because, again, self-respecting computer scientists, all our logs are base 2. So this becomes log of n, right? For an array, in fact, let me go ahead and move over to the actual notes here. So the analysis here is that for an array of size n, we perform at most log n comparisons. Right? Contrast that with linear search, which was n in the worst case, or n divided by 2 comparisons. Right? If I were to graph these out, what would it look like? What would n look like? It would look like something like this. Now, if you look at the average case, then that's going to be the same thing, but n divided by 2, so is slightly lesser slope, but it's still a linear function. Right? This is linear search, worst case. This is linear search on average case. The best case scenario with linear search is you get lucky and you find it the first place you look, and you only have to make one comparison. Right? What would, and then this is as n tends towards infinity, right? What would logarithm look like? On this scale, it would look virtually indistinct from the x-axis. But you can see that it would, that the growth rate actually goes down as you get larger and larger n. Right? Last time we looked at the idea of when we doubled the input size. When we go from an input size of n to 2n, we performed roughly with linear search twice as many comparisons. What about with linear search? If we only perform n comparisons with linear search, or with binary search, excuse me, and we double the input size, how many do we do now? So pull out your log identities from your memory. Right? Log of AB is equal to log of A plus log of B. Same thing here, but I will switch them around so that I have log n plus log of 2. Remember that it is base 2. That's equal to log n, as many comparisons as you were making before on an input size of n. But now, what about this part? Plus 1. Right? Put this into perspective. If you go from 1 million to 2 million, with linear search, you would end up doing about 1 million more comparisons. With binary search, instead of 1 million more comparisons, you're only doing one more comparison. Right? That is huge. That is an exponential speed up. Let me show you the consequences here. Right? So I've got this demo here. Don't worry about the details of this demo. I just want to show you that in practice it is terrible. The linear search versus binary search, it is absolutely clear which one wins. So here I will show you I will talk about the experiment setup here. I'm going to create a unique array, and then what I'm going to do is I'm going to go through that array and try to find out if it has any duplicates. All right, I'm just going to call this function called contains duplicates. Let's take a look at what that looks like. All right, here it is. So for each element, right, for the ith element, I'll assume that that's the element. And then what I'll do is I'll go through all the remaining elements. And if I ever find an element that is a array sub j that is equal to that element, I will return true because it has a duplicate. If I have 5 here and I go through the rest of them, and oh, there's another 5, stop and report that. There is a duplicate here. Otherwise, if I get through every single element and they only ever appear once, I will return false. There are no duplicates. It does not contain any duplicates. Why am I going from I equals 0 up to n minus 1? Well, that last one, I don't need to check for a duplicate. The very last one, it's by itself. I don't need to check for a duplicate because there are no further elements to the right. Why do I start at I plus 1? Well, I don't want to say that, oh, here's 5. Oh, and it's its own duplicate. I don't want to do that. I want to only check all the elements after it. Right? Why don't I want to check any of the elements before it? Maybe there's a 5 before I got here. then if that's the case, I've got a 5 here and a 5 here, I would have found that when I looked at this one first, right? So I don't need to go over the entire array once more, but it is going to be terrible, right? So this is basically linear search right here, right? On an array. This sub part right here, 78 through 82, that's a linear search, okay? So let's go ahead and run this and see what the results are. I think I put this in a different folder. Duplicates. Yep, all right, let's run it. And I'm, by the way, this creates a random array of guaranteed to be unique elements. So it should say no, there are no duplicates every single time, right? But they are going to be different every single time. I can go ahead and up the size of the array to 100, right? And all of this stuff is completely, you know, not even observable, right? It goes by like that. When I go up to 1,000, still, it goes like that. When I go up to 10,000, okay, did you see that was kind of taking a little bit longer, right? And 100,000, wow, now it's taking a noticeable amount of time. Let's understand why, all right? So I'm going to actually go ahead and formally time this thing. Let's go ahead and go with 1,000. This is reporting the actual time that it took to execute that. So 0.002 seconds. All right. Let's go ahead and go with 10,000 because that's going to be a little bit more substantial and give us something to actually work with here. All right. So 0.16 seconds. If I run it multiple times here and get an average or something like that, it'll be between 0.15 and 0.20 seconds. All right. All right. So good enough as a sample. Now suppose that I go up to 20,000, right? What is your prediction on how much longer this will take? Yeah, go ahead. It's going to be at least double the size, the time, right? But remember what I'm doing is I'm doing a linear search for each element. So a linear search is going to be n comparisons, but I do it for the first one. Are there any duplicates? For the second one, are there any duplicates? For the third one, are there any duplicates? Fourth, fifth, sixth, seventh, eighth, right? So I'm doing n comparisons, roughly n comparisons, right? For n values. So that's not linear anymore. What is it? For each element, you do a roughly n comparisons. How many elements are there? N. So altogether, it's going to be n squared, about n squared. Of course, we're not doing the entire thing every single time. You can take out a factor of 2 there, I think, but that was it. So if I go from 10,000 that took roughly 0.15, 0.20 seconds, just round it off, then how much time is it going to take now? All right, go from n to 2n. Again, you are doing n squared operations. What's going to happen now? 2n squared, which is equal to 4n squared. Before you were doing n squared, now you're doing 4n squared, so it's 4 times slower. All right? With linear search. Okay? So let's go ahead and execute this and see if we get something like this. 4 times 0.2 is going to be slightly less than 1 second. Yep, no, slightly more than 1 second. But if I do this multiple times over and over again and take an average, you're going to get something that looks way more like 0.8 or something like that. Right? It's taking a little bit more time because, of course, I do have to build the array. I should only be timing this right here. All right, help me out. If we go up to 40,000, let's say that it was taking 1 second for 20,000. Now 40,000 is going to take how long? It was taking 1 second before. Doubling it will be 4 seconds, right? Double, 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 double. It's 4 times, 4 times, 4 times, 4 times. So if it's 1 second, that'll go up to 4 seconds now. So double it again. 80,000. 4 seconds becomes 4 times 4, 16 seconds. 1, 2. little bit more. There we go. 14 seconds. I was counting way too fast. I had reached 20 in my head, right? But at roughly about almost 16 seconds, right? This is almost a one-to-one analysis here, right? Let's predict, without actually running it, Wolfram Alpha, what would happen if we went up to 1 million? 1 million. 1, 2, 3. Divided by 80,000, right? So in other words, we would go up by a factor of 12.5. Going up by a factor of 12.5 squared is going to be 156 times slower. 156 times slower of 16 seconds to hours will mean that this would take about, well, not full hours, but 41 minutes and 36 seconds. Roughly. That's just an estimate. So should I do it? Right. Well, if that's the only thing you want to do for the rest of the time, then sure. Right. But we've got other things to do here. What I've got here is an alternative. Contains duplicates good. So let's take a look at this. Q-sort. I wonder what that is. It's sorting, right? It's sorting the list. Why? So that we can do a B search. What is a B search? A binary search, right? And I'll talk about all that later because it requires us to use a comparator function here, which is something brand new, right? But otherwise, instead of doing a linear search for each element, I'm doing a binary search for each element. So let's go back over here and look at the contrast. Before we were doing n comparisons on n elements. Now we're doing log n comparisons on n elements. Or n log n. Right? Now, hopefully you understand that this is such a slow growing function, you don't really even have to pay attention to it. Right? In fact, we have a special name for this. If you could ignore this logarithm factor here, then this would be a linear function. Once you add that logarithm factor, it's so small that you can call it a quasi-linear function. Right? It's almost linear, and for all intents and purposes, treat it as linear. Right? So let's go ahead and see what performance we can get out of this now. So remember last time it was with, I didn't even try it for 1 million. What was 80,000? Let's do it for 80,000. 80,000 was 14 seconds. What do you think it's going to be now? Instantaneous. Right. We predicted that 1 million elements would take us 40 minutes. It takes you 0.1 seconds, 0.17 seconds. Right. So hopefully you see the huge divide here. And as you get more and more, as you get larger and larger arrays, the difference is going to become huger and huger. Right? Bigger and bigger. Right? This is because this is an exponential speed up. So what we started out with is that a sorted array has a structure that you can exploit. Right? And you see how good it is to exploit that structure. Right? Keep that in mind for your project because we formulated the project and we formulated the data such that there's going to be a large amount of data, and if you do things naively with linear search or brute force stuff, it's never going to compute, right? You're going to take hours, days, weeks, months to get it done, right? Computationally. So keep in mind binary search. We will come back to this next week. What I want to do is focus on this. I love that structure. I loved seeing it sorted. How do we do that? Right? So let's talk about a sorting, right? How would you sort something? Let's go back over here. I already got it. There we go. There's an array. Sort it for me. As a human. Yeah, sure. Yeah, from lowest to highest. Sure. All right. So you told somebody told me to put 0 first. Why? Explain to me what you just did. You went through it and you chose the smallest element. And then what did you do with it? You put it over here. Right? Now, obviously, a computer needs to have a little bit more instruction than just go through, find the smallest element, and put it at the front. It might look something like this. You go through, All right, 4. That's the smallest element I've seen so far. 9, that's not smaller. 4, that's the same. I'm not going to update that. 102, not smaller. Oh, something smaller. Circle that. There's the smallest one I've found so far. Keep going. Oh, I found something even smaller. Circle that. And now I'm at the end of the array. What should I do now? I need to put it at the beginning. So I should swap these. And it leads to something that looks like this. There we go. 0. 42 is now down over here. And the rest of it remains the same. 9, 4, 102, 34, 12, and 2. Now what do you do? The same thing, right? But should I start here? Because that's already where it needs to be. Don't move it. You gave it its home, leave it there. So start at the next element here and find the next minimum element. Well, okay, 4 is small, so we'll start out with that. 9 is not smaller. 4 is the same, it's not smaller, not smaller, not smaller, not smaller. Oh, fine, there, 2, that's smaller. 42 is not smaller, I'm done. What do I do now? Swap these. And so it ends up looking like 2 and 4. And continue. When do you stop? When everything is where it belongs except for the last element. Well, wait a second. What about that last element? What ends up being the last element in this particular example? 102, right? And if you've sorted the first 8 of them, and 102 is right here, do you need to sort 102? It's right where it needs to be. Right? This is called selection sort. Right? Why is it called selection sort? What are you selecting? You're selecting the smallest. So selection sort. Right? The basic idea is that you go through and find the smallest element. And you can go ahead and sort in descending order if you want to. That's just go through and find the maximum element and put it at the end. Or go through and sort it in ascending order and then just reverse it. Right? Lots of ways that you could do this. Go through and find the smallest element and swap it with the first. Right? I'm going to go ahead and put this onto the next line. Right? Then go through the remaining n-1 elements and find the smallest among those. Right? Swapping it with which one? The second. Right? It could end up being that if it's already sorted, that's already where it needs to be, and you end up swapping it with itself. So be it. Right? Repeat until you have the first n-1 sorted. Right? The last element will be where it needs to be. Excellent. You might have seen this before. I think if in your arrays lab, we had an implementation of selection sort in there as a preview of what sorting might look like. So let's do that over here as a exercise. I'm not going to be returning anything. So let's go ahead and call this selection sort, because that's what it is. Should I take a const int star array? No, unlike binary search where you're just going to search through and find the needle in the haystack, you're not going to mess up the haystack, if that's possible. Right? Here you are going to mess up the haystack. Right? In fact, you're going to mess it up by sorting it. Right? So it cannot be constant. If you wanted to implement a version of this where you created a deep copy, you sorted that deep copy and then gave it back to you so that the calling function had both, you could do that as well. Right? Int n, and there's no key here because we're not searching for anything, we are sorting it. Okay? Let's go ahead and implement this now. So what's the basic idea again? For each element, for each index 0 up to ... question mark, find the minimum element for each index I equals 0 up to whatever, among a sub I and a sub n minus 1. Right? I'll do it like this, LaTeX code kind of. Right? So if I've got the, let's visualize this actually, yeah. So, sorry, go over here. So let's visualize this. We're going to jump into the middle of the algorithm, okay? A0, A1, A2, dot, 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 A, I minus 1. Suppose that at some point, this has been sorted, okay? Now you've got A sub I plus 1, dot, 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 up to A sub n minus 1, the last one, all right? This is unsorted. So what you're going to do is you're going to find the minimum. Find the min. That's step 1. Step 2 is what? Once you've found the minimum, say that it's a min, what are you going to do with it? You're going to swap it with a sub I. Right? So swap a sub I and a sub min. Right? Once you've done that, then that incorporates a sub I over here into this part. And now that's sorted. Right? I don't want to do it like that though. There. Right? Now it's part of the sorted area. Right? And you continue to do this until dot, dot, dot. Elements A0 through AN minus 2 are all sorted. Now tell me about that a sub n minus 1, sorry. It's where it needs to be. You're done. So I should run I from 0 up to what? N minus 2. Good. 4. Int I equals 0. I is traditionally I would go up to n minus 1, right? Because it's a strictly less than. But I don't need to stop. I can stop one short. There's no harm in going all the way to the end and looking at that last element and seeing, okay, well that's the minimum. I'll go ahead and swap it with itself, but there's no point. Right? I plus plus. Right? Now I'm going to find the minimum among a sub I through a sub n minus 1. So what I'm going to do is I'm going to keep track of the index. Int min index. Where should I start it? If you're starting at a sub I and going through over here, we'll go ahead and just assume that this first one is the minimum. By the way, you could put this into another function if you wanted to. Right? Find min within range. Here's your array. Here's the range I up to j. Kind of like you did with contains. Does it contain the element, or does it contain it within the indices I to j? Right? So the min index here will be at I, and then we'll find the minimum among the rest of them for int I. Can I reuse I, by the way? Not inside here. So let's go ahead and use what's next? J. I'll start that somewhere. J is less than n. I do want to go all the way to the end here to see if that's the minimum. J plus plus. Where do I start? Do I start all the way back at the beginning? Nope, that stuff is sorted. Don't touch it. Do I start at I? Well, I could, but I've already started there, up here. So I'll start at I plus 1. Right? And if I find something less, if the array sub j is less than array sub min index, I've found something smaller. And so I update my min index to be j. Right? Now, at that point, oh, sorry, there we go. Now here I need to swap a sub I and a sub min index. Right? So how do I do that? This is an integer array. So int temp is equal to array sub I. That frees up array sub I to put in array sub min index. Oops, got to spell it right though. And then that frees up array sub min index to take on the value of temp. Right? And at the end of the day, return. You've modified the array. So now let's come back over here and see if this actually works. What I'll do is I'll roll this back so that we have an unsorted array. And then I will call my function, selection sort on numbers and n, the size. And then just to make sure, I'm going to print it out. For int I equals 0, I is less than n, I plus plus. Put this into a function, reuse it, print array. In fact, I think you already have one, or you've been given one at least. Printf, %d, comma. We won't get fancy on the formatting here. We're just going to print it all out. But I do want to make sure that it's on a different line, though. There we go. So GCC. Didn't make any syntax errors. Great. Yay. Sorry, I was trying to pat myself on the back. Forgot that my front was before that. All right, so a dot out. I don't want to time it now. Let's go ahead and kick it down to just 10 here. All right. Not duplicate. Sorry. I need to go back to the other directory. GCC search.c and demo.c and film.c. All right, and run it. And 0, 2, 4, 4, 9, 12, 34, 42, and 101. Before it was not sorted. Now it is sorted. Definitely works. And by the way, the binary search still works too, as long as you're searching for something that exists. It should find it at that old index 7. Right? Excellent. So, selection sort. All you have to do is write your own selection sort every single time. Right? So, you want an array of doubles. You want an array of films. You want an array of students. You want an array of characters. You want. Should I be cutting and pasting, cutting and pasting, cutting and pasting? No, we don't want to do this. Not only that, and go all the way back over here to integer. Right? Not only that, but this is actually a terrible sorting algorithm. Right? Again, I'm not going to do the full analysis, but I think in the pre-prepared videos I might do it. But I'll just tell you right now, selection sort makes about n squared comparisons. In fact, the two loops that we just wrote for selection sort, I running from 0 up to n minus 1, j running from I plus 1 up to n, we just saw those in action. I running from 0 up to n minus 1, j running from I plus 1 up to n minus 1. Right? And how bad was that? Very, very bad. Right? Why? Because when you go from n to 2n with n squared, you go up to 4n squared. When you go up by a factor of 100, what happens? When you go from n to 100n, right? So you go from 1,000 to 100,000. What happens here? 1,000 to 100,000, right? Squared. What is that going to be? 10,000 times slower. Right? So if it took you 1 minute, or say that it took you 1 second before, now it takes you 10,000 seconds. How many is that? 10,000 seconds to hours? Almost 3 hours. Right? Now go up by another factor. So instead of going up to 100,000, go up to 10 million. 10,000 times 10,000 is what? 100 million times slower, right? So 10,000 seconds. 1, 2, 3, 4, 5. There we go. Now you're not talking about hours anymore. What are you talking about? Years, right? Yeah, 31 years. So 31 years to sort something that's only 10,000 or 10 million integers or 100 million integers? Not happening, right? So is there a better way? Yes. There's something called quicksort. Why do you think it's called quicksort? Because it's fast, exactly, right? It is quick. So here's the idea. We're not going to go through a full implementation or anything like that. I'm just going to show you what it looks like. Okay. So let me go ahead and pull in that example array that we had. There we go. Right. So like binary search, it's a divide and conquer strategy. So what we're going to do is we're going to choose this as our what's called a pivot element. All right. So basketball just started, right? So what is your pivot foot in basketball? You can take 2 steps, right? And then once you've got the ball and you're not dribbling, 2 steps, that second step, that becomes your pivot foot. You can't take that pivot foot back up until you've passed the ball, correct? Right? Now, how often is it actually called? Nah, that would be a very uninteresting game if every single travel was called. But anyway, that's the idea. You pivot around that foot. You can keep that foot anchored to the floor, but you can move around. You can rotate around that foot, right? This is going to be the pivot element. And what we're going to do is we're going to look at all the other elements, and we're going to pivot around this element. We're going to look at 4. 4 is less than 42, so where should it go? Over here on the left, right? Or your left, right? 9 is less than 42. So where should it go? Over here on the left. 4 is less, so it goes onto the left. 102 though, that's greater, so where does it go? To the right, over here. 102, there we go. 34 is less, so it goes over here. 12 is less, 2 is less, and you end up with an array that looks like this, and an array that looks like this. Now where does 42 go? Oh, sorry. 0. I don't have room for it. 42 goes right here where it should be. Right? Everything to its left is less. Everything to its right is greater. Now all we need to do is recursively call quicksort and sort this array. But guess what? An array of size 1 is what? Done, sorted. Right? An empty array, by definition, is sorted. So all we really need to do is focus on this part over here. Let me go ahead and rewrite it because you're right, it is bad. 4, 9, 4, 34, 12, 2, and 0. There we go. Once again, we will choose a pivot element here, 4, and we'll pivot around it. Where does 9 belong? On the right. 4 belongs, you can break ties arbitrarily. We'll go ahead and put them on the left. So 4, 34 belongs over here. 12 is greater, so it belongs over here. 2 is less than 4, and 0 is less than 4. So you end up with an array that looks like this, and an array that looks like this. And you don't actually create these arrays, by the way. You just pass in a bunch of indices. Right? Okay? Now, you continue on this one, you continue on this one until you get down to an array of size 0 or 1, at which point you're done. Again, this is a divide and conquer approach. This is quicksort. There are a couple dozen sorting algorithms. Some of them are good sorting algorithms, some of them are bad sorting algorithms. Like I said before, selection sort is going to make about n squared comparisons. But quicksort, now there are some caveats here. Quicksort can degenerate into selection sort, in fact, on bad inputs if it's already sorted, or if it is sorted in reverse order, you end up with a quicksort, or you end up doing nothing. Don't worry about that. In the average case and in the best case, it ends up doing n log n comparisons, just like our good duplicate check contains duplicate good. I had to name it something else, and well, it's good, it's better, right? I could call it quick, I guess, right? Just like quicksort is called quick, right? So, same idea as before. If I go from n to 2n, and it's only taking me log n, and it goes to 2n log n of 2n, sorry, then about how many more comparisons, how much more work am I doing now? only about twice as much work. Now, there is a lower order term here, granted. It's going to be plus 1, whatever, right? Plus a logarithmic factor. But forget about that. This is what's most important. You're only doing twice as much work. So twice as slow. Here, if I double it, double ends up being 4 times as slow. And if you go up by a factor of 10, this one will be only 10 times slower. This one will be 100 times slower. So you start to see the difference here. Now let's go back to our contains duplicate good. Right? Again, I'm not going to implement quicksort. I'm not even going to implement any other sorting algorithms. There's bubble sort, there's merge sort, there's Tim sort, named for a guy named Tim. Literally, that's what it's called. And insertion sort, and another half dozen sorting algorithms. If you're interested in looking at all those, great, go ahead and find a YouTube video with all these nice visualizations. I think I've even seen some where there are Dutch dancers that very, very quickly you get tired of it and they dance around and they simulate the sorting algorithm and they sort themselves in 1, 2, 3, 4, 5, 6. Right? You get tired of that really, really quick. Right? But anyway, what is the first thing I do? Q-sort. What does that stand for? Quicksort. Exactly. Don't roll your own. Don't write your own searching and sorting algorithms. Use what's built into the language. Both Q-sort and B-search are in the standard library. Use them. Now the only question is, how do you use them? Okay. So let's take a quick look at how you might go about doing this. So, searching and sorting in practice. Okay. In general, you do not need or want to write your own searching and sorting algorithms. Right? It's just too much work. It would be lots of copy pasta for different types, right? Lots of testing, right? Lots of debugging, etc. Lots of work. Don't do that. Don't roll your own. Don't roll your own implementations. We use this colloquially in computer science all the time. Don't write your own solution when you can just use a library, right? Don't reinvent the wheel is another nicer way of putting it, right? But don't roll your own is perfectly nice. We're just talking about tobacco, right? That's where it comes from, right? What are you rolling? You're rolling your own tobacco cigarette, right? So that's where the term comes from, at least, right? Don't roll your own. Let the cigarette company do it for you, right? Don't smoke either, though. Right? It's bad for you. If you're going to, then vape, but then don't vape either. Right? All right. So don't roll your own. Just use what's in the standard library. Okay. But that begs the question of how do you go about using this, and how does it solve that copy pasta problem? How can quicksort be used for an array of integers? How can quicksort be used for an array of doubles? How can quicksort be used for an array of films, whatever we were doing, right? Well, the answer is it doesn't know anything about the elements, right? So the way that you do this is that Qsort and other built-in algorithms know how to sort. They just don't know how to order, right? If they don't know anything about the elements, what the elements are in the given array. They could be integers, doubles, films, etc. Right? Qsort needs to be told how to order those things. Right? I'm keeping that general and generic. Those things. It could be films. It could be integers. Basically, you need to be able to tell Qsort, here's this thing and here's this thing. Here's A and here's B. What you need to do is you need to tell it that, oh, A comes before B, or B comes before A, or they're equal. Sound familiar? Where have you seen that pattern before? No? Here's a string, here's a string. How do I say that this string apples come before bananas? Or apple, capital A, comes before lowercase a apple? How do I compare these two strings? ASCII values, and that function is called strcmp. CMP is short for comparison, right? We need to give it what's called a comparator. A comparator function solves this problem. Right? What is a comparator function? A comparator function takes two generic things and returns an integer with the following contract. It returns something, and I'm emphasizing that, something negative. If, here, two generic things, I'll call it A and B, right? And it returns something negative if A comes before B. It returns 0 if A equals B. And I'll put that in quotes there because what does it mean to equal? Well, if there are two integers, equals equals is enough. If there are two strings, strcmp returning 0, it means that they're equal. If you want to compare them and ignore the case, uppercase, lowercase, or whatever, use that str case cmp, right? If they're two films, this film and this film are the same if they have the same title and the same director and the same whatever. Right? These two things are the same film if they have the same Internet Movie Database rating, right? Whatever your criteria happens to be. And then finally, it returns something positive if A comes after B, right? Or what's another way of putting that? B comes before A. That's the general contract. Let's take a look at a visualization of this. Right? There we go. So I've got an array here, and that's going to be an input to this generic black box sorting algorithm. Ultimately, that's going to be QSort for us in C. Right? This sorting algorithm knows how to sort. It knows that, oh, okay, this thing comes before this thing, or this thing comes before this thing, so they're out of order, so I need to swap them, like in selection sort. Or if it's quick-source implementation, here's my pivot element. This is less than the pivot element, so it goes over on that side, or this is greater than the pivot element, and so it goes over on that side. It doesn't need to know anything about these two things, other than they go like this, or they're equal, so that it knows which side to put them on. Right? That's where this comparator comes in. We plug that in as an additional input. So we've got an input here, which is an array of stuff. We've got a comparator that does know about that stuff. This comparator would be written for an integer. It would be rewritten for a double. It would be rewritten for a film, right? All you need to do is, you don't need to re-implement this sorting algorithm, cut, paste, cut, paste, cut, paste every single time. All you need to do is create a new comparator. If you want to sort in ascending order, then you use one comparator. If you want to go in descending order, then you use a different comparator, right? And so you can use the same sorting algorithm to go in increasing order or decreasing order. You can use the same sorting algorithm to sort anything that you want, as long as you give it this comparator here. The sorting algorithm, given A and B, are they in order or out of order? It simply passes it off to this comparator, and it says negative, positive, or 0, depending on the relative order of those two things. And it's able to output this sorted array once it's done. Excellent. That means that you only have to write the comparator algorithm, comparator functions to do this. Let me show you a preview of what that looks like. This is a comparator for integers. Right? It returns a what? An int. Something negative, positive, or 0, depending on the relative ordering of these two things. Does it take integers though? Nope, because it's got to be generic, right? Once you're inside the function, you'll have some assumptions. Those are pointers to things that are integers. By the way, why is it const? So let's walk through each one of these keywords. Why is it const? Are you going to be making changes to A and B? Nope. So I'm promising I'm not making changes to A and B. Void. It's not an integer. It's not a double. It's not a film. Right? It is a void. Void star. Where have we seen that before? Void of generic void pointer. Malloc. Malloc returns a generic void pointer. Simply just a raw memory address. When you call malloc, you put that like int star in front of it, or double star in front of it, or like you did last time, or and you'll do again in your next hack, long star, right? Forcing it to become a particular type. We do the same thing here. I want to force A to become an integer pointer instead. I want to retain my promise. I'm not going to make changes to it, so it's still going to be a const int pointer. Const int pointer. And then, don't try this at home. This is a bad practice, and we'll see why next time. But I dereference x, and I dereference y, and then I take the difference and I return that. Why do I do that? This is called the difference trick, and tricks are for kids, so don't do it, but let's understand why I'm doing it. Suppose that x is equal to 10, and y is equal to 5. What is x minus y? 10 minus 5 is equal to 5, and that is positive, right? So, positive tells you that 10, 5, are they in order or out of order? Out of order, right? If you can't remember, here's a kind of a mnemonic device if you want to. Negative values, if you write A and B, negative values, where do negative values fall? They fall on the left of the Euclidean plane, right? Positive values are over here, negative values are over here. And so if you put A and B on the number line, and A and B, they're in order, then that's negative. If they're the same, that's 0. And then if they're out of order, that's positive. Right? So that's how I remember it. I don't know if that's helpful or not, but there you go. So take another example here. Suppose that we reverse this. X is 5, y is 10. They're in order. 5 comes before 10. If you want to do this in ascending order, right? So x minus y is equal to 5 minus 10, which is equal to negative 5, which is less than 0. They're in order. What happens when they're equal? X is equal to 5 is equal to y, which is equal to 5. X minus y is equal to 5 minus 5, which is equal to 0. They're the same thing. Right? That's why it's called the difference trick. Tricks are for kids. Don't do it. Why? What is negative 2.147 billion minus positive 2.147 billion? So they're in order, by the way, negative and positive. But what's the, well, let's ask Wolfram Alpha, because I have no idea. I'd have to really think about that. Like negative 4.294 billion. Is that going to fit into an integer? Nope. What's going to happen? Overflow, underflow, and it becomes positive, telling you that they're out of order when they're in order. Right? So don't do that. It is susceptible to overflow, underflow. Instead, do this. Here, I'll comment this out. Instead, be explicit. Right. Explicit, there we go. If dereferencing of x is less than dereferencing of y, they are in order. Return something negative. Give me something negative. Excellent. Negative 1. Why not negative 42? Why not negative 3? Okay, fine. Go ahead, but why be weird, right? Else if dereferencing of x is greater than the dereferencing of y, they are out of order. Return something positive. In this case, 1. Else, return 0. They are equal. Being explicit like this means that you are not susceptible to overflow and underflow. Excellent. All right. So we're going to talk more about how this comparison function is actually done and the patterns for it. And then finally, how do you pass a function off to another function? CMP was the function's name. Did you see that? Function's name is CMP. I should have called it like int CMP or something like that. But I'm passing the name off to another function. I'm not calling the function. I'm not doing this. I'm actually giving the function as part of the input. That's a function pointer. So we've seen pointers plenty of times now. A pointer can point to an array. A pointer can point to one thing. What else can a pointer point to? Any piece of memory ever in the entire computer. What's stored in memory? Data, integers, functions. I can have a pointer point to a function. I can have a pointer point to the square root function, and then make it point to something else, right? I can make the square. You can't do it with very easily, but you can make the square root function point to the sine function, and then really screw things up, right? Because now every time you call the square root function, you're actually getting the sine instead, right? So you can have you can have pointers point to functions so that you can pass them off to other functions. And that's where we'll pick it up on Monday. All right? All right, have a good weekend.